In this next problem, we're going to use the same steps as we did before and find the equilibrium potential sign first. So in this problem, we have C plus and T minus. Since we have more on the outside in the extracellular fluid, it's going to want to go inside into the intracellular fluid for both ions. So more positive charge is going to come in here, making it positive, giving us a positive 50 for C plus. And more negative is going to come into the cell, giving us negative 100 for T minus. So now that we have these two numbers, we can find our resting membrane potential. We just take positive 50 and negative 100 and we multiply that by their relative permeability at rest. So 50 times 0.15 is going to give us 7.5. Negative 100 times 0.85 is going to give us negative 85. And we just add these together. Negative 85 plus 7.5 is going to give us negative 77.5. And that is for the resting membrane potential. The next part is finding the peak action potential. So for that, we just take positive 50 and negative 100 again, and we multiply each by their relative permeability at the peak. So this is going to be 0.75 and this is going to be 0.25. And we just plug that into a calculator. 50 times 0.75 is going to give us 37.5. And now negative 100 times 0.25 is going to give us negative 25. So 37.5 minus 25 is going to give us 12.5. And it's going to be for the peak action potential. Now that we have these two numbers, we can now find the total excursion. And that's just going to be the absolute value of the resting membrane potential. So that's going to be 77.5 plus the absolute value of the peak. So that's going to be 12.5. So we just add those together. Giving us 90 for total excursion. Now the next step is finding the threshold. So that's going to be the resting membrane potential, which is 77.5, plus or minus the total excursion, times the percent. So the percent is located right here, 10%. So 90 times 0.10. So now, since we want to move this number towards 0, we're going to have to add it instead of subtract. So 90 times 0.10 is equal to 9, and 9, and then we're going to take negative 77.5, and then we're going to add 9, giving us negative 68.5. For the threshold. Now we have all the data to use for our chart. We have a resting membrane potential of negative 77. Our threshold is negative 68. And our peak is going to be 12.5. So to figure out what to do next, we just look at the example. Given the conditions, please draw action potential in the space so that the sub-threshold is applied for 5 milliseconds. So what that means is we're going to start here at the resting membrane potential, and then at the 5-second mark, or the 5 millisecond mark, it's going to reach the threshold. So the threshold here is 68. So it's going to reach this part. So threshold is applied for 5 milliseconds. The peak action potential is reached in 5 milliseconds. So in 5 milliseconds, it'll be 10 milliseconds. And it's going to hit this mark right here, which is the peak. So after the peak, it will return to resting membrane potential in 10 seconds. So 10 seconds later, it'll be 20 milliseconds. It'll return back to the resting membrane potential, and then it will level off. So here we have the resting membrane potential, the threshold, the peak, and finally the return back to the resting membrane potential. So here there is depolarization because it's moving in a direction towards 0. It's also capable of repolarization because it returns back to the original spot. And there is no hyperpolarization because it does not go below the resting membrane potential.